Okay. Let's see here. All right, there we go. All right, you had some time to think about it, so let's do some of these together. So how about A3? So 3 is odd. So we do 3 minus 1 over 2, which is A1. A1 was A. And then we have an A afterward. So A3 is AA. Right, similarly, A4. 4 is even, so this is going to be A2 multiplied by B. And A2 was AB. So this is ABB. We already did A5, so let's skip on to A6. 6 is even. So this is going to be A3, just dividing by 2 to get the 3 there, multiplied by B. A3 was AA. So this is AAB. All right. A7, 7 is odd, so we subtract 1 and then divide by 2. So we get A3 again. And this time we multiply that by A. So that is going, sorry, I'm learning the technology here. There we go. Just removing my chat window. Okay. So that is, so A3 was AA, so this is AAA, right? A8, okay, so A8 is just going to be A4, because remember we're just dividing by 2 because it's even. A4 multiplied by B, and A4, where was A4? A4 is ABB, so this is going to be ABB. B, right? A9 is just going to be, well, 9 is odd, so we might subtract 1, divide by 2, so 9 minus 1 over 2 is just 4. So we have A4, and we multiply by A, because 9 is odd. So A4 times A is A, B, B, A. All right. And then the last one is A10. So let's write that out. A10, 10 is odd, so we're just going to have A5, and we're going to multiply that by, sorry, 10 is even. We're going to have A5, multiply that by B. So A5 was ABA, so we just have ABAB. Does anyone have any questions about any of that? Oh, question. Let's see. Okay, Lewis is good on questions. So because Lewis is good on questions, we will move on. All right. Thank you, Lewis. Here we go. So the second part, we're going to use part A to determine A17 and A21. All right. So let's get back to the drawing board. You know, so A17, 17 is odd. So we are going to subtract 1 and divide by 2. And that's going to give us A8. And then we are going to multiply, since n is odd, by A. All right, and then A8 is A, B, B, B. So this is going to be A, B, 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 A. All right. Similarly, we can do A21. So, does anyone want to tell me what A21 is? If you'd like to, you can do it, and I'll just fill it in.
I can.
Go ahead.
Okay, so it's odd, so it's A of 21 minus 1 divided by 2, which ends up being A10.
Mm-hmm.
A10 is AB multiplied by A, so it ends up being ABA.
All right, thank you. AB, A, B, A. And that's right, A10 was AB, and then we just tack on an A because 10 or 21 is odd. All right, so that was part B. So there's one more part to this. If at any time there are any questions, just interrupt me and we'll talk about it. So gonna get back to the mouse, erase some stuff. So we have an eraser. So let's erase. Okay, so A315 is that. Wow. And we want to compute A630. So let's do that really quickly. So 630 is even. We divide that by 2. We have 315. So A630 is just going to be, so A630 is just going to be AN over 2 times B, or A315 times B, and A315 is this. So let's not write it down just because of time, but it's that thing. And then we're going to multiply by B. So that would be A630. And then A631 would be done in a similar manner. And then Michael has a question. Do we need to be any more explicit than this for showing our work in the homework assignment? I would say probably not, but James has taught this class before. So James, if you have any thoughts, you can go ahead.
No, for this problem, that'd be enough work to show.
All right, so that's this problem. So just this is getting a little bit of practice with sequences, and of course, if you've looked at the homework, there's some more sequence-like problems on the assignment. Are there any other questions about this problem? All right, let's do the next one. And if you do have any questions about this problem, you can always stop me. So we are erasing. All right. Going back to the mouse, closing the chat, getting the drawing board up. All right. So this problem, we are given two logic statements. A is this statement, P or T and P or C, where T is a tautology, that means it's always true, and C is a contradiction, that means it's always false. And we also have B, which is the statement P. And we would like to show that these two statements are logically equivalent using this table. So take a minute or two to do that, and then we'll do it together. Oh, chat question. Oh, thank you, David. That's good. Thank you. I appreciate that. I will use that. All right, let's do this. So here goes. We have statement A, which is this statement, P or the tautology. Remember, the tautology is always true. And P or the contradiction. The contradiction is false. It is a false statement. All right. So we want to show that this is logically equivalent to P. So let's start. P or the tautology. So we look in this table here, and we can find something that's logically equivalent to. And so if we have a keen eye, then we would identify this entry of the table. And that says that P or the tautology is just the tautology. Okay, so that means we can rewrite this statement as T, the tautology, and P or the contradiction. All right. And then let's do this again. So does anyone want to tell me the next step that they might take? Oh, there's some people in the chat saying something. Oh, do we need to write out the name of the property, or is it referencing it with its letter sufficient? Yeah, you can reference it with its letter. That's fine. I mean, that's totally fine. Yeah. So yeah, what I think someone said the next step, which is just someone go ahead. Do you have a question, or do you want to say something?
I was just saying use identity next.
Yes, that's exactly right. All right, so yeah, so we're going to use identity. Yeah, yep, that's right here. So this is just equivalent to P. All right, so we have T and P. Okay, so I'll just state out what these entries of the table. We used row I, then we used row D. All right, and then we have the tautology and P. Okay, so if we go back to the identity, we have P and the tautology, but that's not quite the tautology and P. But the AND operation has commutativity as a property, so let's use it. And then we'll be able to go ahead and use the identity again. So in particular, we're going to use A. So A will allow us to rewrite this as P and T. That's A. All right? And then finally, we use the identity again, which is this one here. And that gives us that this is P. All right. Are there any questions about that entire process?
So we need to explicitly do commutative, like
Yep.
state it. We can't just interpret.
In my personal opinion, I don't really think it's necessary. If you know that the AND operation and the OR operations are commutative, then I personally don't think so. But I don't run the class, and so whatever the lecture Dr. Cohen says goes. And I know in the last lecture section, James did use the commutativity property explicitly. So I would say go ahead and put it in there just to be clear. So it shows that you understand that for the OR and the AND operation, the commutative property holds. Because, for example, not all operations have that property. For example, the division operation does not. So A divided by B and B divided by A are not necessarily the same thing. So I guess we want you to be explicit in this course.
Okay.
Okay. Are there any other questions about this problem? Okay. Then let's move on. David taught me about the delete operation, and that's what we're going to use. Okay, boom, magic. Now, let's move on. All right, now we have a sequence. This looks a little bit more like a homework problem that we've seen. So we want to do three things. Compute the next term in the sequence, find a closed form for the sequence, and give a recursive formula. So go ahead and take a couple minutes to think about this, and then we'll do it together. All right, let's do it. So, what is the next number in the sequence? Anyone can just shout it out.
18.
Yep, thank you. So, all right. Now we need to give a closed formula. So to do that, yes, Lee, that is the correct answer. So let's when you're generally trying to do this, you want to try to identify a pattern. So let's think about how we might arrive at that. This one is let's just think about how we would get there. So the first term is 3 times 1. So this is a1. The second term is 3 times 2. And the the third term is 3 times 3. Okay, so you need to relate the indices to the numbers in the sequence. So in this case, it's kind of easy to do that. Well, it may not be if you're just seeing this for the first time. So, but in general, you want to try to relate the index of the sequence to the number that you see. So that's how to do that in this case. We see that we just take the index and we put it there and then multiply by 3. So as Lee said, an is just 3n. All right. And then if you want, you can either shout it out or just put it in the chat. What is the recursive formula? Yes, Colton has it right. Make sure that you put the first term as it actually is. So because the first term has no previous term, so there is no recursive formula for it. So we in particular, so as Colton exactly said correctly, a1 is 3, and then an is an minus 1 plus 3. So the thing to remember here is that the first term is a1. It has no previous term, so we can't use the recurrence to write out a1. So we have to write out a1 explicitly. And then in the previous section, there was some chatter about, in general, if we know the closed form, how can we try to find the recursive formula? Because you have some more difficult problems in the homework. So let's kind of look at the general strategy here. So we know that with the closed form, an is 3n. And we know that an minus 1, is there another, we know that an minus 1, sorry, is 3 times n minus 1. So somehow when we're trying to find a recursive formulation, we want to relate an and an minus 1. So here, well, if this is 3n, the straightforward thing to do is to distribute. So we have 3n minus 3. So now we know, oh, well, 3n is an. So we now know a relationship between an and an minus 1. And then we can just add 3 to both sides, and we've got our equality and our recurrence. Question, go ahead.
Oh, yes, I have a question. Can we just use an minus 1 and we can get the same formula?
Yeah, if you just say that an minus 1 is 3, then you found the relationship. I think is that your question? What exactly is your question?
Yeah, here we have an equal to 3n, and we have an minus 1 equal to 3n minus 1.
Mhm.
And can we simply use an minus an minus 1 equal to 3?
Yeah, and that's basically what we did here. What you determine, so you're saying you determine that an minus 1 is equal to 3, and then in general we want to know what the next term is in the sequence from the previous term. So what we would like you to do, and on the homework and in the quizzes, is to come up, is to write an in terms of an minus 1. So you've determined that an minus 1 is 3. Go ahead and put an isolated on one side. So we're actually saying what an is. You know, this equality implies that an minus 1 plus 3 equals an. So yes, you need to determine a relationship between an and an minus 1. And what we would prefer, or what we would like you to do, is isolate an and solve for an. So put it on one side alone.
Oh, okay.
Yeah. There's some questions in the chats, so let's take a look at those. Do you recommend normally starting with closed formula, then trying for recursive? In some cases, I found myself able to figure out recursive, but not closed. Well, I'm not really sure. I think it depends on the problem, but I think it can be difficult to go from a recursive formula to a closed form. So I would recommend starting with the closed form and then from there trying to get to the recursive formula. Because then you can follow a strategy like that. If you know the closed form, then you can write out an, and you can write out an minus 1, and then you can try to find the relationship. If you just know the recursive form, it might be difficult, depending on the situation, to get back to the closed form. And then the other question is, will all problems given have both a recursive and a closed formula, or is it possible it won't have a valid formula of each type? I think there are sequences that don't have a recursive formula that are just defined with a closed form. So I don't think that having a closed form means we need to have, there must be an equivalent recursive form. I'd have to think more about an example, but James, do you know about one offhand, a simple one offhand, where there would be a closed form but not a recursive form?
Not off the top of my hand, no, but I know there's some that exist.
Okay, so I'll think about that after class, Alec, and then or a little bit later if we have extra time, and then you know, does Fibonacci have a closed form? Does it?
Yes, I believe it's actually in like a problem in the book
Okay.
to find the closed form.
And then, yeah, it's like exponential of some sort. Okay, Alec, won't that not always work for some complex sequences than addition? Well, just
By that I meant the process that David suggested. Like, you can't always just subtract the an from an minus 1, right?
No. Yeah, you might not. It might involve multiplication instead. It could. So that's not a general thing you can do, but sometimes it will work to find the relationship between the two. But sometimes it'll be some strange multiplicative relationship, like let's see here. So you might have something that looks more like an is you know, like 3an minus 1, something like that, plus 2. So there, you might not be able to get a clean looking difference between an and an minus 1. All right. Yeah, and then the Fibonacci sequence, it's something exponential. We could also go over that if we have time. We could figure out what that would be. It's 328, so we have I think one more problem in this sense at 345. So let's move on to the last problem. Okay. And then I'm going to use that clear on my drawings. Okay. So this one, we're going to be using symbolic logic to write out these statements. So we're going to have P as one symbol represent that A is truthful. Q is the statement that B is truthful. And R is the statement that C is truthful. All right. And now we're going to write out the following English statements using symbolic logic. The first one is that A is lying and B or C is truthful. So let's do that one together. Okay, so A is lying. A is lying is the opposite of A being truthful. So if P is A being truthful, A is truthful, then not P is A is lying. So there's not P. Okay, the next part we have this and. So that means we'll use a logical and. And then we have the statement that B or C is truthful. So that we can rephrase that as B is truthful or C is truthful. So that would be Q or R. Are there any questions about that one?
I have a question.
Go ahead.
So the reason why the and is on the outside as opposed to in the parentheses is because it takes precedent, or is it the order that it's in the sentence?
Yeah, so these are two separate phrases. A is lying and then we have this totally separate truth statement, which is that B or C is truthful. So if we put A is lying and B is truthful together, we would be representing a different, the meaning would be different. We can write out what that would be. I'm not sure if this is helpful to answer your question, but if we had put A is lying and B is truthful together, that would look like this. So not P and Q or R. So what this would be saying is that A is lying and B is truthful or C is truthful.
Okay.
So that would be a little bit different. And to show that it's different, you would work through the truth table. So, yeah. So notice that, well, no, it's fine. Let's keep going. So there's B, C, and D. So just go ahead and take like 5 minutes, and then we'll go through those last three.
I had a quick question.
Go ahead.
So for part C, to my understanding, are we supposed to write a truth table, or is this just a logical statement we're
You can
writing?
just write out the logical symbols just like we did for part A.
Okay, I just wanted to make sure.
All right, let's get started on these 3 problems, just so that we can make sure that we get through them. So let's do B first. So we have that A and B are lying, or A and C are truthful. So we have this or in the middle, and the first thing we have is A and B are lying, and the last thing is A and C are truthful. Okay, so A and B are lying. That's A is lying and B is lying. And remember, if A is lying, that's the opposite of A being truthful. So this first thing we have here is not P. And then we have that B is lying, so that's not Q. So and not Q, the and is here. So and not Q, right? And then we have an or. A and C are truthful. So that would be P and R. So that's A is truthful and C is truthful. So P and R. All right. Are there any questions about part B? All right, let's do part C. So this one, at least 2 people are telling the truth. At least 2 people are telling the truth. So this can happen in 3 different ways. It could be that person A and person...
No, I think there could be 4 possibilities, like AB, AC, BC, and ABC are telling truth. So there are 4 possibilities.
Yeah, yes. So that's true. And when we write this out, we don't need to express that case, but you need to keep it in mind. So thank you for that. I think was that David?
Yes.
Okay, yeah, thank you. So we have that A is truthful and B is truthful, so that would be P and Q, right? Or it could be that A is truthful and C is truthful, that would be P and R. And then we have, could be that B is truthful and C is truthful, so that's Q and R. All right, so David mentions a really good point, which is that there's actually a third case which represents at least 2 people being truthful, and that would be all 3 people being truthful. But we don't need to write that out. So if we were to, so this is one statement, and if this statement is true, then at least one pair of people, one pair of two people is truthful. Now, it could be that three people are truthful, but we only needed to make a statement that was logically equivalent to at least two people being truthful. So if we want to be really, really rigorous, then in our mind, what we should do is show that this statement here is logically equivalent to the, actually, that's going to be confusing, that it's logically equivalent to the following statement, where we have the three pairs, P and Q, or P and R, or Q and R, or Q and R. Oh, sorry, I did a, oh, that should not be an or, that's an and. Second, that's an and. So again, we represented the three different pairs, P and Q, or P and R, or Q and R, and David's point was that well, that's actually logically equivalent to this statement, where we have an or, P and Q and R. So that means that all three people are truthful. So if this statement is true, then this statement is true. So if this statement is true, then at least one of these pairs of people are truthful. And then, so certainly, then one of these pairs is truthful, and so since it's a logical or of statements, the whole thing is truthful. And we can also go in the other direction. If this statement is truthful, then either one pair of people is truthful, or all three are truthful. And if all three are truthful, then certainly one pair, in fact, all three pairs are truthful, and so this statement is true. So the two statements are the same. So you can just write out P or Q, or P and Q, or P and R, or Q and R. All right, there's one more here, which is exactly two people are telling the truth. So in this statement, it could be that A is telling the truth and B is telling the truth, but R is not telling the truth. That would represent exactly two. So let's write that out. That would be P and Q and not R. Okay. Or it could be that P is telling A is telling the truth and C is telling the truth, but B is not telling the truth. So that would be P and R and not Q. Or it could be that B is telling the truth and C is telling the truth and A is not telling the truth. So that would also be exactly two. So this is Q and R and not P. So in this case, we have to have these negation statements here to make sure that we're representing exactly two and not three people telling the truth. So there's 2 minutes left. Are there any other questions? All right, I'll stick around for a couple minutes. That's all of the content that's in these slides. So if you want to go enjoy your day, then please do. And I will get a little bit better at the technology as we go. So I apologize for my technological ineptitude today, but that will improve.
Thank you.
Yes, thanks.
Thank you.
Hi, I have one quick question about recursive sequences. So when you're writing a recursive sequence, are you allowed to incorporate the use of n in the like definition of the sequence, if that makes sense? Because I've seen it somewhere, but I don't know if that's like legal.
You mean like an plus 1 equals an plus n, that kind of thing?
Yeah, that kind of thing.
Yeah, that could happen. There's
Okay.
nothing against that.
Okay, cool.
Yeah.
All right, thank you.
Yeah. There was a question in the chat. Am I allowed to ask a homework question? You? Yeah, go ahead.
So for the first question on the homework set, we asked for a recursive formula, and are we allowed to do like square, like put an minus 1 under a square root?
You are technically, but I don't know if that's going to be super helpful with that one. I need to remind myself of the problem. And so I think I remember what it is. I'm going to write it out, and then you can verify if it's the right problem. Let me see here. I just need some space, so let me clear this. Okay, so that one was an equals 2 to the n over 2 plus 1. Is that right?
Yeah.
Okay. So generally, to answer your question, yes, it could happen that an is under a square root. Absolutely. That is totally possible. And that, I think that might be okay here. So just let's kind of work through this a little bit. So an minus 1 was 2 to the n minus 1 over 2 plus 1. Right? Okay. So then we want to express an in terms of an minus 1. And so let's do the algebra. This is 2 to the n over 2. Oh, that's good, because that shows up here. So that's good. And then we have minus half. Okay, so that's something we can take out. Okay, so what we have is this. The minus 1/2 is that's 2 to the n over 2 divided by the square root of 2. And then we're adding 1. Okay, so we're almost there, but something, it's not right, because we
Hi. Sorry, I was on hold so long, I forgot what I was gonna say. So I had.
Wait. Is some that one, that must have been someone else?
Oh, sorry, it was my roommate.
Oh, okay, sorry. Actually, I think you can do it. Yeah, okay, that's fine. All right, so we're almost there. This is fine. So we have an minus 1 equals 2 to the n over 2 over the square root of 2 plus 1. So we're almost to something reasonable. I think I did this in a silly way, but that's fine. We can keep doing it like this and see what happens. So so there's an minus 1. Well, let's subtract 1 from both sides. So we have an minus 1 minus 1. That's 2 to the n over 2. All right, over the square root of 2. And so let's multiply by the square root of 2. All right. And then, so, well, we're almost done. What's the last thing we have to do here?
Replace that with an.
Yeah, so yeah, basically, so this 2 to the n over 2, it's not an, but it's almost an. So all we have to do is,
An minus 1.
yes, it's an minus 1. So so this is equal to an minus 1, and then we can add 1 to both sides. So we have this, and then let me erase this, and that's it. So that's that problem.
I think I made a algebra problem, an algebra mistake.
Yeah, well,
That's why I didn't get it right.
well, it could be that you did do it right, and that, you know, like this looks a little, oops, undo that. That this looks a little different, but anyway, this is the idea of this problem. So.
Okay. Well, so when I list the first 5 terms, I got like square root 2 plus 1, and square root 2 to the second plus 1, and then square root 2 to the third. So at first I did an minus 1 times 2 on the square root and then plus 1.
Oh. Yeah, well, no, I mean, yeah, it's just there is a square root of 2 there, and you just keep on raising it to a higher power. So, yeah.
So will that work? I'm just curious. I totally understand what you taught me, but I'm just curious the answer I got at first. Would that work?
Can you say it to me again? I'll try to understand it better, and then
Oh,
write it down.
Oh, okay.
So say it again. I'll just write it down.
Oh, okay. I had a square root. I have an minus 1 times 2 over square root, and then that thing plus 1 is equal to an.
2 times 2 over the square root of 2?
No.
Square root.
Under.
Like this?
No, it's an minus 1 times 2. Yes.
Plus what?
Plus 1.
Oh, this?
Yeah.
I don't think so. Just because these are not equivalent. It would have to be that this would be equivalent to that. So and I don't think they're not equivalent. These are not equivalent, just because we have a square root of an minus 1 here, and this is an minus 1. So in this case, yeah.
But I got that from the first 5 terms, like, because all the, what's that called? So like a1's like equal to square root 2 plus 1, a2 is equal to square root 2 to the second exponent and then plus 1, and then a3 is like square root of 2 to the third exponent and plus 1.
Well, you're right about what you just said is right, but I think that this, what was a1? What they're all like this. So the first one is the square. A1 is the square root of 2 plus 1, and a2. So if according to this formula here, it would be the square root of 2 times the square root of 2 plus 1 plus 1. According to the formula, according to this formula, then this right here.
Wait. I realized what's wrong. I forgot there's a plus 1.
Oh, okay. All right.
Oh, okay.
So this,
That was dumb.
okay, are you okay now? Does that,
Yes, I'm totally okay.
this doesn't look good.
Oh, I get it. Thank you.
Yep. All right, I have class in a couple minutes, so I have to go. If anyone has any other questions, I think James has office hours today, and he's very clear, so he will be very helpful. So have a good day, and see you next Friday.